It's just a matter of time until another asteroid sets course for the Earth. In the worst case, its impact will release the force of millions of Hiroshima bombs. A catastrophic force of nature.
There's an incredible amount of objects out there, and they're moving at unimaginable speeds. On long time scales, the probability of something hitting the Earth is high, if not very high.
When such a threat looms, scientists from around the world take up the fight.
An object of around 150 meters in size can create havoc not only where it impacts, but also in a large surrounding area. And for an even larger object, it can affect the whole globe.
Our only hope of preventing the catastrophe: high-tech computers, satellites, and rockets.
We have quite a few options to prevent such a disaster from happening, but what we really need is time.
The race begins, in which nobody knows who will win. With today's technology, do we stand a chance against a planet killer from space? Chapter 1, Discovery. How quickly do our early warning systems detect danger? Chapter 2, Combat. What options do we have to defend our planet? And finally, Chapter 3, Showdown. How prepared are we when the impact is imminent? We'll find out on Facing Forces of Nature. Asteroids. The origin of this force of nature lies in the formation of our solar system. Back then, about 4.6 billion years ago, planets formed from a cloud of dust and gas. Remnants of the time are still buzzing around our sun today. Every year, 40,000 tons of it burn up in our atmosphere. But every 100 years on average, slightly larger meteors hit us. Some 25 meters in diameter. Larger celestial bodies over 100 meters are considered potentially dangerous. They occur every few thousand years. Once in a million years, asteroids over a kilometer in diameter hit us. And every 100 million years, the so-called dinosaur killers strike, threatening to wipe out all life on planet Earth.
So it's very unlikely that an asteroid will hit Earth, but it can happen, and over a long enough time period, it's going to happen at some point.
It all starts with an inconspicuous point of light somewhere in the sky. An asteroid that could unhinge our world.
Every day, telescopes and radar systems are detecting new objects in the sky. Most of them are harmless, but some of them might not be.
The battle, man against the force of nature, begins. The most modern surveillance systems in Europe, the USA, and Asia sound the alarm at the slightest danger. Telescopes record all new objects in the sky fully automatically, 365 days a year. Their target, so-called NEOs.
Near-Earth objects are objects which are within around 1.3 astronomical units of Earth. 1 astronomical unit is the distance between the Earth and the Sun. So near-Earth objects are objects within around 200 million kilometers of Earth.
At 200 million kilometers, they feel infinitely far away. But asteroids travel at an average of 20 kilometers per second. This speed equals a car on the highway traveling at 72,000 kilometers per hour. For a long time, all life on Earth was helpless in the face of such catastrophes. as in the Chicxulub event. 66 million years ago, a 10-kilometer chunk of rock hits the Yucatan Peninsula in Mexico. Its impact released the energy amounting to millions of Hiroshima bombs. It caused one of the largest mass extinctions in history.
Everything was destroyed in the immediate vicinity of the impact crater, but beyond that, life changed dramatically all around the Earth. What caused that was that the climate of the Earth changed quite significantly after this impact and led to the death of something like 75% of all the species on Earth. Of course, it's impossible to say for sure what would happen to humanity if such an impact took place today, but if the same climate changes occurred, it would be hard to see how humanity could survive that.
But impacts of smaller asteroids have also caused catastrophic consequences. 50,000 years ago, a 50-meter in diameter asteroid in the Arizona desert releases the energy of 150 Hiroshima bombs. It left behind a crater 1,200 meters wide and 170 meters deep. Enough to wipe out every major city in Europe.
I think the damage that an asteroid would cause depends quite a lot on how big the asteroid is and how fast it's moving. A relatively small asteroid might only affect the local area, but a big asteroid, say the same size as the one that wiped out the dinosaurs, would completely change life on Earth as we know it.
The most recent significant impact occurred just over 100 years ago. In Siberia, a fireball explodes at an altitude of 8 kilometers. It releases an explosive force equal to 1,000 Hiroshima bombs and uproots 60 million trees over an area of roughly 2,000 square kilometers. Dangers like this can happen again at any time. Are we able to stop them with 21st century technology?
The real advantage we have today is that we have the technology to detect anything coming towards us early on. And it's with the help of telescopes that we can actually detect asteroids that come close.
The first key advantage. Today, we are able to detect most asteroids years before they strike. Optical telescopes detect almost any celestial body and are able to determine factors such as brightness, size, and speed.
Telescopes can look at particular regions of the sky at very high resolution. But the problem is they can only ever look at specific areas. They can never get a global view of the skies. What we can do, of course, is to scan the sky and put all the pictures together into one big picture where we can identify the larger objects at least.
The most powerful telescopes in the world are also known as asteroid watchers. Among them is the Pan-STARRS in Hawaii. Its photos have a resolution of 1.4 billion pixels. But despite all the high tech, their field of view is limited.
The problem with the telescope is that it can only see one patch of the sky. It only has a limited field of view. And that means you can only look at one place in the sky at a time. And you can do that sequentially. You can look at one spot and then another spot and then another spot, but you simply can't look at the whole of the sky at the same time. And that's a real limitation.
In order to detect all dangers in time, scientists are developing even more efficient telescopes. One of the most important projects is FlyEye. Its task is to capture significantly more parts of the universe simultaneously. The trick: the optical system works similarly to the compound eye of a fly. It combines the images from several lenses to form one large image.
This really reduces the possibility that we're missing a planet killer.
But despite all progress, one weakness remains. From Earth, we can only monitor the sky at night. The solution lies with space telescopes. They hover in the Earth's orbit. Like the Wide Field Infrared Survey Explorer of the U.S. space agency NASA. Space telescopes scan space for infrared radiation. Asteroids heated by the sun gradually emit this radiation and thus reveal their position.
The problem with visible wavelength telescopes is that near-Earth objects can often be very dark, or they can be between us and the sun, so we wouldn't be able to see them. If you look in the infrared, you can actually detect them still, because they are still illuminated by the sun, so they will be warmer than the surrounding. So even if we cannot see them with an optical telescope, we will be able to see them with an infrared telescope.
So with the technology we have at hand today, we can see anything coming towards us within the next 100 years.
In the first phase in battling the force of nature from space, the combination of ground and space telescopes is our best tool.
So when asteroids approach the Earth from behind the sun, we can only see them using telescopes. And that means that only the because it's the daytime, only the brightest objects stand out in the sky, and meteorites and asteroids don't tend to be that brightly illuminated. So we're essentially blind to asteroids that come from the direction of the sun.
Looking directly at the sun is nearly impossible for both humans and telescopes, which greatly hampers the ability to see what is between Earth and the sun. There, the gravity of Venus and Mercury captures stray asteroids quite frequently. They are also potential planet killers. They move along on partially unstable orbits and continue to surprise science. One of these impacts occurred on February 15, 2013, in Russia. In the city of Chelyabinsk, a barely 20-meter diameter chunk from space sparks an energy corresponding to 600 kilotons of TNT. Its massive blast wave leaves 3,700 buildings damaged. The warning time, practically zero.
This was an object that appeared out of nowhere, so we were very lucky that it didn't hit us at a different angle and cause even more destruction. But what the episode highlights is the danger of us being hit by something potentially very dangerous without us having any notice in advance.
New, even more efficient telescopes should prevent such catastrophes as best as possible in the future. But which asteroid is actually a danger to us? Or is it just a simple celestial phenomenon? The International Asteroid Warning Network, a task force of the United Nations, is responsible for this. It analyzes the trajectory of asteroids all over the world. They can approach from anywhere. However, the origin of most asteroids lies between Mars and Jupiter. There are probably more than 10 million of them buzzing around. The planet's gravitational force normally holds them firmly in their spell. But occasionally, asteroids collide and rip each other out of their orbit, so to speak. They then fly uncontrolled through space, and the worst case, towards Earth. Further afar lurk other dangers, comets. They originate at the very edge of our solar system, between the planets Uranus and Neptune, in the so-called Oort cloud.
So many of the objects in the Oort cloud are too dark to be properly seen with the telescopes. So a lot of what we think we know about it is actually speculation.
Scientists believe there are billions of chunks of rock and ice here. Despite the extreme distance, if they are ejected from their orbit, they too can pose a danger to Earth. It just takes a little longer. Light, traveling at 300,000 kilometers per second, needs up to 1.5 years to journey between Earth and the Oort cloud. Mathematically, a comet needs at least 6,000 times longer. So its trek to us takes about 9,000 years. In other words, if a comet hits the Earth tomorrow, it was already halfway here when the Egyptians built the pyramids.
Obviously, this is only a numbers game. In reality, if you want to calculate the time it takes for an object to reach us, you have to take into account the exact orbit and the gravitational fields that the object encounters on its way.
If comets approach our sun, there is a danger that they will cross the Earth's orbit at some point. When comets hit the Earth, the effects are catastrophic.
Comets also aren't to be underestimated. They can be up to kilometers in size and can travel incredibly quickly. The energy that something has depends quite strongly on how fast it's moving. And so these incredibly fast-moving comets pack a lot of energy.
Relatively recently, in 1994, it appeared that a comet may soon strike the Earth. The catastrophe failed to materialize, but astronomically speaking, it misses us only narrowly. Its debris hits Jupiter. It is the first observed impact of a celestial body in our solar system. And the starting signal for the international planetary defense. It's a wake-up call for science and humanity. Today, celestial scientists around the world are exploring numerous theories. The most promising first step, a reconnaissance mission.
If we have enough time, we can start a reconnaissance mission. And the aim is to really get to know our enemy better. But enough time in this context means at least 10 years.
To get to know the enemy better, a probe is sent into space. It approaches the celestial body up to a few kilometers. High-resolution onboard cameras scan it, and thus create a complete 3D model. The probe then analyzes the surface composition of the celestial body using infrared spectrometers and records its composition using radar technology.
When looking at asteroids, scientists try to work out their velocity, but also their composition, because ultimately what we need to know is how dense they are and then what mass they have. Knowing the mass will allow us to accurately calculate their trajectory.
In an extreme case, an asteroid with an iron content of over 470 million tons will impact the Earth. Like a cannonball with a mass of almost 70,000 Eiffel Towers. That would be enough to cover the entire area of Germany, France, Belgium, Austria, Switzerland, and the Netherlands. The energy impact, 100,000 megatons. The more we know about the composition of the asteroid, the better we can estimate the danger. Just like its trajectory. The most decisive force in all this? Gravity. Whether on Earth or in space, bodies attract each other.
So many people think that asteroids are these chaotic objects that tumble through space completely haphazardly, but that's actually not the case. They're moving on very predictable tracks, and they follow the laws of physics.
The German scientist Johannes Kepler revealed his findings at the end of the 16th century. According to his investigations, asteroids move on in different, but always elliptical, courses around the Sun. Another important factor, the distance. The further they are from the Sun, the slower they move. The closer, the faster. If all these findings lead to the probability of an impact on Earth, it is time for the heavy guns. The next important achievement of mankind in the fight against asteroids, rockets. Phase 2 begins, combat. And that means throwing the asteroid out of its orbit at all cost. This was long considered nothing more than a theory, until 2022.
Currently, the main way to defend ourselves would be to bring the asteroid off course with a detonation. But the question right now is still, does that actually change the track of the asteroid, or is the asteroid just swallowing the energy?
For the first time, the American NASA and the European Space Agency cooperate. Together, they launch a Falcon 9 rocket into Earth orbit. This in turn catapults a probe into space. On course for Didymos. There, a small asteroid orbits a large one. If the probe hits the small one, it quickly becomes clear how much this affects its orbit.
The DART mission was a very important experiment to try out technologies to change the trajectory of an asteroid. The target was an asteroid that was coming towards us, but crucially, for safety reasons, was not in any danger of hitting us.
The Double Asteroid Redirect Test Project, or DART for short, is the first practical test in the history of mankind. After undocking, 8.5-meter-long solar wings each power the DART spacecraft's ion propulsion system.
The main challenge is to steer a really small unmanned object onto an asteroid, which is many hundreds of thousands of kilometers away, with pinpoint accuracy.
The goal is to slow the small asteroid down by 0.4 millimeters per second. By hitting it directly at about 22,000 kilometers per hour. That's 6 times as fast as a bullet shot from a rifle. The energy released amounts to 2.9 kilograms of TNT, about a quarter of the Hiroshima bomb. And indeed, the probe hits its target on September 22nd. An unprecedented experiment in the fight against the forces of nature.
The DART mission was very successful. A small object that we sent to the asteroid impacted the asteroid and basically gave all its energy and momentum to it. And this was sufficient to change its orbital duration by several minutes.
2 weeks after the collision, initial analyses reveal that the impact shortened the asteroid's orbit by 32 minutes. The deviation, even greater than hoped, a complete success. In an emergency, these few minutes can decide whether an asteroid crosses our orbit years later or not.
The DART mission is the first of its kind. For the very first time, we are actually testing planetary defense. And we know that the path of the asteroid was changed. What we have to find out now is just by how much.
The DART mission is just the beginning. All the data collected are today the starting point for a complete toolbox for planetary defense. Success after numerous, partly bizarre-sounding attempts.
What do we learn from these tests? We learned that it works in practice. So before this, it was all theoretical. We thought that we could fire something from the Earth and hit an asteroid many hundreds of thousands of kilometers away. But it's not until you do that in practice that you know that when it comes to it, it might actually be feasible to do so.
All major theories to protect the Earth from asteroids follow the laws of efficiency, feasibility, and time. And there are many of them. They are based on simple-sounding basic physical principles, and yet they sound quite daring. Like, for example, brushing the asteroid with paint. The idea is based on the Yarkowski effect. Like all planets, asteroids rotate around their own axis. Consequently, only one side is always facing the sun. Therefore, it's warmer than the other. The temperature difference on the day and night side creates a force which pushes the asteroid minimally from the warm side towards the cooler one. If one side of the asteroid were brushed with reflective paint, this effect would be amplified. The result, the asteroid deviates from its original course.
Whether this will actually impact its trajectory is, however, questionable.
Another technique goes back to one of mankind's greatest achievements, the sail. It stems from a simple idea. A solar sail bundles particles, but in this case, light instead of wind. Condensed through a lens, the light is then reflected onto the asteroid, vaporizing part of its surface. This results in pushing the asteroid onto a deviating course. It's similar to the jet engine of an airplane, only much slower. But there's a problem. If you apply current research results to a potential planet killer from space, it becomes clear that it takes decades to sufficiently change the orbit.
This is basically trying to change the track of a very large, very heavy object with tiny, tiny solar particles. So that takes time.
A similar idea is based on deflection by laser beams. Their enormous heat is also supposed to vaporize some of the surface material and thus create a recoil effect. It's important that the source of the laser must be as close as possible to the asteroid, and that presents a problem. Because the further away it hits, the greater the scattering. Even the most powerful lasers developed to date are not sufficient to muster enough energy from Earth to vaporize rock. For example, if we send laser beams to the Moon, which is barely 400,000 kilometers away, the beam fired there would spread over an area of 2 square kilometers. The energy to vaporize anything on the surface, whether moon or asteroid, would be far too small.
It sounds like a great idea initially to use a laser to change the trajectory of an asteroid. Lasers have very high energy bundled light, which could conceivably heat up one side of the asteroid and then change its course. But the problem with lasers is a technological and practical one. Lasers need a lot of energy, and also lasers create a lot of heat, so you need a system to cool them down. And launching such a heavy laser into space will create its own challenges.
The DART mission is the most promising approach to date. But questions remain. Since the composition of the asteroid plays a decisive role in such a mission, it is not certain whether the next mission will also be a success. So, what can we do if even our modern technology, contrary to all foresight, fails? What if telescopes from Earth and space failed to detect the asteroid heading toward our planet in time? What if first attempts at deflection fail, and the impact is imminent? Then, it's time for the most drastic measure of all. Showdown. Is there a last-minute option for fending off a planet killer? The answer is yes, there is. It's an all-round weapon against any kind of extraterrestrial threat. We already know it from countless Hollywood blockbusters.
Ultimately, if we are in an emergency situation, we have to go nuclear, literally.
So according to what we know right now, the nuclear option is the only one that will work on a shorter timescale, when we have less than 2 years.
It is a race where every second counts. Therefore, normal launch vehicles are only of limited suitability. Launch preparations alone take weeks, and the closer the asteroid gets, the more explosive power is required. In extreme cases, dozens of rockets, perhaps over 100. It would require the inventory of the world's available nuclear arsenal. Perhaps everyone would have to band together to eliminate the looming threat in time. Currently, half of all available nuclear warheads are in Russian possession, and only a few less in the USA. A considerably smaller, but perhaps decisive arsenal is also in China, France, and Great Britain. Also in Pakistan, India, Israel, and North Korea. If such a mission is launched at all, the aim of the warheads is not to destroy the asteroid. Instead, their programmed detonation point is a few hundred meters from the surface of the celestial body. The idea behind this is that once the warheads detonate, they flood one side of the asteroid with X-rays and heat it up. The enormous energy with which the material then escapes into space throws the asteroid out of its orbit and ensures that it does not hit the Earth. Instead, it simply flies past it. A direct impact on the asteroid poses unforeseeable risks. Debris could unpredictably reduce large areas to rubble and ash. Therefore, in theory, this method is considered the only option so far when things have to go fast.
Because there are political and societal risks connected to using nuclear weapons, and because it's probably a very more of a diplomatic challenge, who gets to fire their missiles, it's very risky to go that way.
Nuclear weapons in space. The result could lead to overkill should war break out on Earth. The conquest of space during the Cold War began mainly for military reasons. When the USSR launched Sputnik, the first satellite into orbit, the Americans feared above all a nuclear strike from space. 10 years later, in 1966, an international treaty prohibits the use of biological, chemical, and nuclear weapons in space. It is still in force today. Meanwhile, there are numerous plans to re-equip intercontinental nuclear missiles so that they can reach into space. At the American NASA, there is even the idea to equip a spaceship with nuclear explosive devices for a very specific mission. The destruction of Bennu, an asteroid 500 meters in diameter. As things stand today, its course will cross the Earth. The probability of a collision, 1 in over 2,000.
So the number 1 in 2,000 doesn't sound very risky, but if it happens, and it can happen, then the impact will be devastating.
Bennu's mass corresponds to about 615,000 Airbus 350 airplanes, all heading for a single point on our planet simultaneously. So, if it hits us, 60 to 80 million tons will slam into the Earth. But there's a difference. While a passenger plane travels at about 900 kilometers per hour, Bennu is currently traveling more than 100 times faster, at 100,000 kilometers per hour. The good news is we still have time before Bennu could hit us, until September 2035.
In case of objects the size of Bennu, the nuclear option is probably the only one that releases enough energy per mass to reach the desired effect.
That's why the focus is also on rather smaller projectiles, with less lead time. Small enough that we overlook them in extreme cases. Large enough to raise entire urban centers to the ground. The so-called city killer.
Among the near-Earth objects, those hitting us most frequently are the smaller ones. And as we saw from the Russian meteorite in 2013, we cannot actually see them all. These are the ones we need to watch out for. An object the size of 50 meters even can cause catastrophic damage.
The decisive tool in the fight against such hard-to-predict threats from space sounds harmless at first. Planetary radar systems. The Goldstone Radar Complex in California is one such system. It is the largest fully steerable radar on the planet. Its 70-meter diameter antenna initially emits highly focused microwaves in the direction of the asteroid. Large radio telescopes, such as the Green Bank Telescope in the US, capture the reflections and collect enough information to generate a radar image from the data.
To work out the trajectory of an asteroid or comet, we need its precise velocity over some duration of time. And the most effective way of getting that is by looking at it, by tracking it with a radar system for about 1 hour.
Optical observation systems, like telescopes, they can scan large parts of the sky and this way detect objects very early on, so when they're still far away. And then radar systems, they are quite useless at a distance, but once the object comes closer, they are very good at scanning it and following it in detail. So the combination of the two techniques is really valuable.
In the best case, radar observations reduce the positional uncertainty of an asteroid from several thousand kilometers to just a few meters. In addition, with the help of global model calculations and simulations, it is now possible to determine precisely the area to be evacuated. From a diameter of 100 meters, meteorites survive entry into the atmosphere unharmed and strike the surface with enormous speed. The problem is determining where exactly. We sometimes know only hours before.
When a meteorite hits the ground, the result is a crater. Obviously, everything within the crater is destroyed. However, the level of destruction goes far beyond the crater to around 8 or 10 times its radius.
On impact, the meteorite releases its energy abruptly and vaporizes at many thousands of degrees due to the resulting heat. If it breaks up while entering the Earth's atmosphere, the impact energy is smaller, but it also hits a much larger area.
The immediate environment around an impact zone is just completely destroyed. But that's not just around the area of the asteroid, but it also impacts into the Earth's crust, creating a crater which can be many hundreds of kilometers wide. And that whole area can be completely destroyed.
The consequences are extreme, but it's only the beginning of a chain reaction. Depending on the region, this is followed by earthquakes, hurricanes, or even tsunamis, which roll towards our coastlines within a very short period of time.
So what exactly happens depends, of course, on the size of the object that is coming. So at the time it comes close to the Earth, we know that very precisely. And then the next step would be to calculate where exactly the object will hit. And there it's important to be very precise to prevent a mass panic from happening.
Before all facts are known, there is only one thing to do. Wait for the asteroid to come within range of the planetary radar systems, so an exact position can be determined.
Radar systems are great and they're used frequently, but the problem with them is that they can only look at objects nearby. The reason for that is that we send out a signal to the object, to the asteroid and comet, which then reflects the signal back. And the signal which we receive back becomes weaker the further away the object is. So that limits the distance of objects we can actually observe.
An asteroid that we won't know for a long time whether it will hit us or not. What sounds surreal has actually already happened more than once. In June 2004, the optical telescope at the Kitt Peak National Observatory in the USA discovers the asteroid Apophis with its frightening dimensions. Initial estimates figure a diameter of 300 meters and a weight of 30 million tons, enough to completely level all of Europe.
In 2004, an asteroid named Apophis was located in the sky, and it was initially given a 2.7% chance of hitting the Earth in 2029. Now, that might not sound that high, but a 2.7% chance of an asteroid hitting the Earth is by far the highest percentage chance that scientists have ever predicted.
It is not until 17 years later that measurements of the Goldstone radar give the all clear. In 2029, Apophis misses the Earth by only 30,000 kilometers. In space dimensions, that amounts to less than a hair's breadth. At an altitude of 36,000 kilometers, Apophis comes closer to Earth than our geostationary satellites. A grazing shot makes it clear that we are just beginning to arm ourselves against all dangers from space.
This almost encounter tells us that we're only really at the beginning of planetary defense. And if the next asteroid is actually faster than our technical development, the only thing that is left to do is to sound the alarm.
In this case, with the help of radar data, at least the impact location can be determined to within a few meters. Even the time of impact can also be calculated down to the second. When an asteroid will hit us, and with what consequences, is still to some extent unpredictable. The most important thing is knowing about the danger and preparing for it. With even more efficient radar and telescopic systems. And in an emergency, even with missiles equipped with enormous explosive power. To successfully counter this mighty force of nature. All for the protection of our planet, Earth.